What does the computer do after power up? Well, the firmware initializes the some aspects of the hardware, does some checks, and then the operating system takes over. But what does the firmware do? What is the first few instructions that the computer executes immediately after power up? This was my question, and to answer this question, I've downloaded the raw firmware of my computer from the flash memory chip. So I've used a command called flash ROM, and I've downloaded the image of my firmware inside my file system. So this is the firmware that runs every time my computer powers up. What I did then is I run this in qemu, then I connected to qemu through GDB, and I've debugged it to understand what it's doing. So I want to share that with you, and I want to make a video of it for future documentation and on how to do it. So to run this command, I have needed to disable the secure boot feature in my BIOS settings. I don't advise you to do that particularly, because somehow you may corrupt your BIOS when reading it maybe. For me, this computer is somewhat disposable. In short, don't try this at home. Don't try this on a valuable computer. Okay, let's take a look at the file I've downloaded using this command. It's the BIOS backup ROM. It's about 8 megabytes. This file being 8 megabytes indicates that it is a UEFI type of firmware. So it's not a legacy BIOS firmware. My computer is an Intel laptop, so the firmware is going to be according to that. It's going to initialize the Intel operating environment. If we were debugging something like a Linux kernel, we would use qemu system x86-64. But since we are debugging a BIOS program, a firmware, the CPU is supposed to be in a much more basic state compared to when Linux kernel is first run. So we're going to start qemu with this option. We're going to pass it this flag, so it treats our image as a BIOS firmware. We're going to pass the BIOS firmware here, and then we're going to pass it some flags, so the qemu waits for a GDB connection. Okay, I've opened up the qemu now, and let's connect it through GDB. Let's connect it to through GDB without doing anything extra. Let's see what happens. Okay, now we've connected. It says that it stopped at this instruction address. Let's open up info registers to see what is the state of the registers. So we have EAX, ECX, general purpose registers here. We got the instruction pointer. It's FFF0. We got the code segment register, which is F000. Alright, that's interesting. Let's print out the current instructions. So I'm gonna write display 10i $PC, which stands for program counter. So GDB is telling us that the current instruction that would be executed if we called step I is this one. But it doesn't make sense that the first few instructions of a firmware would be like something like this. Add the AL register and the stuff that points at the value in the EAX. And it's doing this like one after another, right? So this doesn't make sense. There's a problem here. The problem is with GDB. GDB doesn't understand that the qemu image that is running at an operating mode called real mode. So what is real mode? Real mode is how Intel x86 CPU is initialized at first, like after power up. So we didn't give that information to GDB, so it's a bit confused. So I'm going to quit GDB and close up my qemu, and then I'm going to run GDB with this command. And this command here, this piece specifically, is going to tell it that what you're connecting to is an 8086 architecture CPU. So I'm going to open up the target XML to show you what it's like. This line here indicates that the architecture of the process that we are connecting to is an 8086 architecture. The 8086 is the original chip of the x86 architecture. It's from 1978. It's almost a 50-year CPU, 50-year architecture. But at the present day, most of our Intel CPUs are initialized. They start their life as acting as a 8086 CPU. So that's kind of funny, right? All right, let's open up qemu and open up GDB with these extra commands. Okay, now those extra commands allow me to monitor the stack, the 8086 registers, and most importantly, the instructions now seem to make sense. They make more sense now, at least. By the way, since we don't have source code, we don't have any choice but to debug in instructions. So at this point, here we can see the general purpose registers, we can see the stack, segment registers, we can see the instruction pointer, code segment. And one thing to note here is the first instruction that the CPU executes resides in this address, quad F0. So we're going to see why that is the case. We're going to see how real mode addressing works. Before going further with debugging instructions, let's take a look at the x86 operating modes. So after a power on, the CPU starts executing in real mode. Real mode is somehow emulating the original 8086 operating environment, which is originally made in 1978. We have like 16-bit general purpose registers, a 20-bit address bus, which means we have 1 megabyte of address space. So if we consider that the BIOS flash image itself is 8 megabytes, we really want to transition to protected mode as soon as possible. The real mode is a very restricted operating environment. But still, the BIOS should implement some software to catapult the CPU inside protected mode safely. So inside real mode, since let's think about this. We have 16-bit registers, but we have a 20-bit address space. How can that be? What you do here is you have some segment registers, segment selector registers, like stack segment, code segment, data segment, and your general purpose registers like stack pointer or instruction pointer would point to the offset from the base of the segment selector. More precisely, what we do here, imagine this is the stack segment base. This one is a stack segment base, and this is the stack pointer. The stack segment base would get shifted to left by 4 bits and added to the stack pointer, and then the result is your physical memory address. So this is how real mode operates. We have no segmentation, no virtual memory. We are directly using the physical memory. Also, segments can overlap. There are no rules, no protection, nothing. So that's what real mode is. One thing to note is I want to give credit to this Stack Overflow answer here. So this is what I use for making GDB understand the real mode operating environment. This person wrote up a very nice Stack Overflow answer, and I'm going to include the link in the description. So the first instruction of the firmware, the first instruction that the computer executes, is a NOP instruction. One thing to note here is the address of this instruction. It's quad F0. So we solve the real mode addressing, and if you take a look at the code segment value, code segment is F000 and IP is F0. So if you shift the segment value 4 bits to the left and add it to the pointer value here, you get the quad F0. So this is how real mode addressing, including the instruction pointer, works. So let's continue with this NOP operations. Now we hit a jump instruction, and it's going to set the IP to FFA30. So it's going to take, okay, let's just execute it. So now IP is FA30, code segment is still F000. The next instruction that is executed is fninit. So fninit is used for initialization of the floating point register. We can refer to the instruction set reference for what it does precisely, but for now it's enough for us to understand fninit initializes the floating point unit. So next, let's execute this instruction. So next we are going to move a double word data from EAX to MM0. So what is the MM0 register? At this point, let's print out the register values with info register command. Okay, so right here we have the general purpose registers, we got the instruction pointer, we got a flag register, we got segment registers, we got control registers, we got an EFO register, and you got XMM registers, but no MM register here. XMM registers are for single instruction multiple data operations. They are not the floating point registers. To print the floating point registers, we can type info float. And here we have got the MM0, MM1, MM2, and etc. These are the floating point data registers. Incidentally, this BIOS program uses the floating point registers as some kind of temporary storage. So it's going to store the EAX value inside MM0 now. Let's go over that. And now the MM0 value is supposed to be 0. But it was 0 beforehand, so it's not very much important. But what is important is the value inside EAX is stored. So if EAX was a different value on initialization, then that will be stored inside the MM0 register, and then we could access it later. Okay, the next instruction is RDTSC instruction. So what does that instruction do? Let's refer to the instruction set reference. RDTSC stands for read time stamp counter. So it's going to read a time, a 64-bit model specific register. It's going to read a 64-bit data. And it's going to store it inside EDX and EAX registers. So let's return to the debugging. And after executing this instruction, I'm expecting to see the EAX and EDX values change. So let's run info registers again. So right now EAX is 0, EDX is some value. Let's step one time. So that instruction is executed. And now EAX is some huge number and EDX is 0. Okay. So what does the program do? It stores these new values, these perhaps valuable information inside floating point registers, inside MM5 and MM6. So let's step over twice and let's look at the floating point registers now. So that huge value in EAX ended up in MM6 and the 0 value ended up in MM5.